Before I talk about the P-series test, I actually want to start off this lesson by finally answering the question, why does the series 1 over n diverge? And this is a series that at the heart of every calculus student should kind of bother them. Because for us, the way we have rationalized convergence is pretty much thinking of, okay, if what we're adding after a while gets so small, if each term is getting so small, like if they're effectively approaching zero, then shouldn't the sum of that series effectively not change after a while? Shouldn't it be a finite value? Shouldn't it converge? But the 1 over n series does not converge. This is what's known as a harmonic series, and this series actually diverges. And previously, I just kind of told you that we would discuss why the series diverges, but I didn't really discuss that. Well, that time has come. So let's actually do a quick breakdown of why this series diverges. And there are a number of different proofs, and I'll actually show you a few more after this. But let's go with kind of the most intuitive reasoning here. And it's actually going to use another similar comparison thought process here. So let's first off write out the series here. What does this series actually look like? Well, when n is equal to 1, my first term is 1. And as I continue on, my next term would be 1/2, and then 1/3, and 1/4. And you see where this is going. It's a pretty simple series to expand out. And I'm going to need a number of terms here just to kind of give the reasoning here, but that goes out infinitely. Now, for a moment, let's just kind of temporarily ignore this one. Let's just ignore for just a quick second, okay? Ignore temporarily. All right, so we're going to ignore that for a second. And what I want to do is I want to actually write out another corresponding series for us to compare this to. And so let's take a look at a series. Again, I'm going to ignore that one for a second, but let's take a look at a series that looks like this. We've got 1/2 as its first term. And then after that, we're going to have 1/4, but we're going to follow it up with another 1/4. And then after that, we're going to write 4/1/8. And I know this looks random and a bit strange, but just kind of bear with me. So let's take a look at this series here. What I want to do is I want to compare that. Well, first off, we've got this first term 1/2, and that is equivalent to the first term in this series with 1/2. All right, so far these two series look like they're going to have equal sums. But let's look at what happens in the next part. If I then group together the next two terms, and the reason why I'm grouping together these two terms here is I know that 1/4 plus 1/4, this is going to be equal to 1/2. Well, compare that to the sum of the next two terms in our original harmonic series. If I add these two terms here, well, you may not be fantastic with your fractions. Hopefully you know it is 7/12, but when we add these up, it should at least occur to us that the sum of these two terms is going to be greater than, and I'll just write out the words to really drive it home, to greater than the sum of these two terms, right? Because this here has a a smaller denominator, which makes it a larger overall value. So 1/3 plus 1/4 is definitely greater than 1/4 plus 1/4. Like, okay, that makes sense. Now let's continue that thought process though. What about 1/8 plus 1/8 plus 1/8 plus another 1/8? Well, the sum of all that is 1/2. And this is where you should start thinking, okay, I think I know where he's going with this. If we add up all of those 1/8 terms, what do we get? Another 1/2. And if we add up these four terms, and don't worry, you don't have to actually add them up to know that the sum of these terms is certainly going to be greater than 1/2 because our denominators here in the first three terms are smaller. So this here is still greater than 1/2. Well, what's going on with this comparison here? I know that in this series here, this entire series here, I could continue to generate a number of terms whose sums are 1/2. So we're effectively adding 1/2 an infinite number of times, right? This series definitely diverges. And if we know that this series above here, this harmonic series, if we know that this harmonic series is greater than this divergent series, just pause and think about that for a second. If I know the sum of this series is greater than the sum of this series, and this bottom series diverges, then absolutely this greater series, if you will, has to also diverge. So this is just a quick way of just kind of getting a sense of why this harmonic series diverges. And if we really wanted to, we open up the possibility of a couple of other different proofs. Let me just show one real quick. If I use the integral test, which we discussed in our previous video, we can actually use the integral test to show that this harmonic series does indeed diverge. So if I find an equivalent function here, and since it's an improper integral, so let's say 1 over x dx, well, what would this look like? Well, this integral would be the natural log of x. Let me just write x here, evaluated from 1 to b. And if we evaluate this limit at those bounds, we have the natural log of b minus the natural log of 1. Well, right off the bat here, what is the limit of the natural log of b? And I should probably put parentheses around there. What is the limit of the natural log of b as b approaches infinity? Well, this is going to approach infinity. Therefore, this series diverges by the integral test, right? The natural log of x increases as x approaches infinity. So now that we know that this series does indeed diverge, it begs the question, okay, when would this start to converge? Well, we saw in our previous lesson when we discussed the integral test, we know that the series here, 1 over n squared, this one converges. This series converges. So a very natural question that you might ask yourself is, okay, so what is that magic number for the degree of the denominator? When do we go from diverging to converging? And that's precisely the question we ask ourselves when we answer, when we discuss the p-series test. So let me just go up here and state what the p-series test first says, and then I will just do a very quick proof on it. So the p-series test says, any series where p is a positive constant in the denominator of a harmonic series, right? Or it has the structure 1 over n raised to the power of p. Well, if that p value is greater than 1, then it is going to converge, like we saw with the example of, again, 1 over n squared. Since p is equal to 2 here and it's greater than 1, this series does converge. However, if your p-value is in between 0 and 1, 0 is less than p, which is less than or equal to 1, meaning it can be 1, then that series diverges, like we just saw with the harmonic series. And think about for a second, why can't p be less than 0? Why can't p be negative? Well, that would then mean that your n raised to the p power moves to the numerator, and for sure then you have something that we may not be able to find the limit of. So let's quickly discuss a proof for the p-series test. Let me just do this on a separate page, and this won't take very long. So for the p-series test, let's discuss a very quick proof for this. Well, let's look at this structure for this series, 1 over n raised to the power of p, where again, p must be greater than 0. And we're actually going to use the integral test here to actually prove the p-series test. That's why we discussed that first before the p-series test. So by the integral test, let me write that, by the integral test, we're going to let f of x be raised equal to x to the negative p power, or 1 over x to the p, okay, however you want to think about it. Well, let's set up that integral. So since it's an improper integral, we're going to say, let me go ahead and fix that, 1 upper bound b, x to the negative p dx. What is this? The limit as b approaches infinity of x to the negative p plus 1 over negative p plus 1. And all I'm doing there is applying the power properties for integration, right? We're going to increment the numerator by 1 and divide it by the new incremented power. So that is being evaluated from 1 to b. So let me rewrite that, clean that up just a little bit now with us evaluating this at our bounds. So this would be b raised to the, let me just rewrite that negative p plus 1 as 1 minus p over 1 minus p, minus 1 raised to the 1 minus p over 1 minus p. And we can kind of temporarily just disregard what's going on here in this constant, right? Because this we know is going to give us some constant, right? That's not really going to be affected by what's happening here as we're looking at the limit as b approaches infinity. Now let's think about this for a moment, right? Or as your old elementary school teachers would say, put your thinking caps on. What is the only way that this series could converge? Well, this series would converge if, since we're looking at the limit of this as b approaches infinity, the only way that this could converge is if this here gets dropped to the denominator, right? Because otherwise that numerator is going to continue to grow without bound. So the only way that this could converge to a value is if this b to the 1 minus p power moves to the denominator. Well, again, what's the only way that that can move to the denominator? That's if 1 minus p, if the entire difference here of that power, if that is negative. That's the only way it moves to the denominator, is if this is negative. So it converges, right? That if it converges if 1 minus p is negative. Well, if we finish solving that inequality, what do we get here? Negative p is less than negative 1. P has to be greater than 1. And that's where you do a pencil drop. Boom, right? We've just shown that the only way that that series or that function could converge is if p is greater than 1, which is why when we go back now to our p series test conditions, we say that when p is greater than 1, that series will converge. If it is between 0 and 1, it will then diverge. So let's just do a couple of very quick examples with this. So real quickly here, number 9, which is on the back of the notes sheet. First off, we want to establish what is our a sub n. Well, it looks pretty simply like it's just 1 over n times root n. Well, if that's the case, we can rewrite this series as the following. What is n times root n? Well, that's the same as 1 over n to the 3/2 power. So from here, we'd say that our p-value is equal to 3/2, which is greater than 1. So this series converges by the p-series test. And that's it. This is an awesome test because it's really, really simple. The only limitation about it is that it's only used really for a very specific type of series where it follows the form 1 over n to the p power. But that's a kind of your golden ticket. Once you start to see it follows this structure here, then you are good to go. Let me skip over number 10. Try that on your own. I think it's a pretty straightforward problem, especially once you understand number 9. But let's move on to number 11 real quick, just because it provides something slightly different. Well, right off the bat, actually, I noticed that I've got 3 and 2 in the numerator and denominator respectively, and I can just move that to the outside. So I can rewrite this as 3/2 times the summation of this series. Now let's look at this for a second. This is n to the 1/3 divided by n to the 2/5. If we use our power properties, then we can rewrite that as 1/3 minus 2/5. And what does that give us? Well, 1/3, that's 5 over 15, minus, what is that, 6 over 15? That's negative 1 over 15. So let's rewrite that. So we got 3/2. And again, this 3/2 isn't really going to change anything. So we can write this as 1 over, well, n to the 1 over 15 power, because it was negative 1 over 15. Well, from here, we can say, all right, our p-value is equal to 1 over 15, which is less than or equal to 1. Well, actually, don't need less than or equal to. It's just less than 1. Therefore, this series diverges by the p-series test. Okay? All right. So now I would encourage you go ahead and try some of these other problems on the front page, because if we look at numbers 3 and 4 on the front page, we'll notice that both of those problems can be done either using the integral test or the p-series test. All right, so good luck with those.